This video contains the notes for sections 10.4. Things we'll cover in these notes are the so-called divergence test, the integral test, and the what a p-series is. And we'll also talk about the limit comparison test, which is actually, in our book, it's in section 10.5, but I'd like to talk about it in the context of what a p-series is. And we'll do kind of a light version of the limit comparison test. I'll show you how to use it without having to do all the nitty-gritty stuff to actually prove something. So anyway, what are these tests for? These are tests to see if a series, an infinite series, converges or diverges. First of all, the divergence test. This is a very simple test. The divergence test basically says this. If the limit as n approaches infinity of the terms of your infinite series is not equal to 0, then the series diverges. If you think about that for a minute, this should be very obvious. In other words, you could also say that for a limit to converge, the terms, for a series to converge, the terms are going to have to be approaching 0. You can't add up infinitely many things that aren't going to 0 and expect to get convergence. The other part of it is if the limit as n approaches infinity of the terms is 0, wouldn't it be nice if that just meant it converges? But it doesn't mean that. This is a necessary but not sufficient condition for convergence. So if the terms are going to 0, then the series might converge. At least it's got a chance. And that's where the other tests come in. But the first thing we would want to check before we start investigating whether it converges or not, we want to make sure that it's got at least got a chance. So real quick, here's an example. Does the series let's say does this series converge? Let you pause and think about that for a minute. If you paused and thought about that for a minute, what you should be thinking about, or maybe you did think about, is what happens to these terms as n approaches infinity. In other words, what's the limit as n approaches infinity, sorry, that looks like an h, as n approaches infinity of n over 2n plus 1. That's an infinity over infinity. You could use L'Hopital's rule, or you could recognize it as a precalculus limit where the powers are the same on the top and the bottom, 1 top and bottom, so that limit's equal to 1/2. These terms, this series cannot possibly converge because the terms are approaching 1/2. It's as if we have something it's a whole bunch of terms, and we could write some of them out. When you plug in 1, you get 1/3 plus, when you plug in 2, you get 2/5, plus you plug in 3, you get 3/7, 4/9, and so on and so on. And as you go way, way out in the series, you get things that are getting really close to 1/2, 1/2, 1. They're not actually equal to 1/2, but as n gets really big, the 1 fades off into obscurity. and it doesn't make much of a difference, and you get things that are really close to 1/2. And if you just keep doing that forever, clearly this is not going to all add up to something if you keep adding 1/2. So it's going to keep getting bigger and bigger and bigger. So it diverges. It failed the divergence test. So that series diverges. Let's talk about, well, let's do one more example with that. How about this? Does the sum from n equals 1 to infinity of 1 over 2n converge? And you might notice, just like with integrals, sums are kind of like integrals. We could take the 2 to the outside. That's the same as 1/2 times the sum from n equals 1 to infinity of 1 over n. And this limit, the limit as n approaches infinity of 1 over n is equal to 0, right? So we would say maybe it didn't fail, right? But in fact, does this converge? In section 10.3, we talked about this is the harmonic series, super important series. And so we would say no. But it's not because of this test. It's because it's the harmonic series, or 1/2 times the harmonic series. So no, but not because of this test. We got this far, right? It had a chance, but then when we looked a little bit closer, we recognized it was just a version of the harmonic series. And we know that that diverges, but just barely. All right, so more about that in a minute. Let's talk about the integral test. And we'll just call it the integral test, but it's the integral test for convergence. Integral test says this: if you can find a function, which is usually very easy to do, where f of n is equal to a sub n for all n, that basically just means take the inside of your sum and turn it into a function. Think of it as a function. I'll show you how to do that in a second, but it's very easy. Then either the integral from any number you want, we'll say 1 to infinity, that does not have to be a 1, of f of x dx. That's an improper integral, right? And your sum either they both converge, and remember, for it, when one of these things exists, that means it converges, or they both diverge. So in other words, you can, by evaluating an improper integral, you can determine whether one of these things converges or diverges. So let's look at the harmonic series again. So consider the sum from n equals 1 to infinity of 1 over n. In other words, the harmonic series. And then let f of x equal 1 over x. So I just took this and made it into a function. So when I plug 1 into this, I get 1 over 1. When I plug 1 into this, I also get 1 over 1. I'm just making that function here that does the same thing as the terms of the series. So we're going to evaluate the integral from 1 to infinity of 1 over x dx. The antiderivative of 1 over x is natural log x from 1 to infinity. That's equal to the natural log of infinity minus the natural log of 1. And natural log infinity that's going to infinity, albeit slowly, minus 0. So that's infinite, so this diverges. Therefore, since the integral diverges, so does the series. Let's try another one. It's a good review of improper integrals too, right? Let's consider n equals 1 to infinity 3 over 2 n squared. Well, I'm going to simplify this and make things as easy as possible for myself. The 3 and the 2, those are just constant multiples, and I can take those to the outside. That's the same as 3 halves, the sum from, you don't have to do this, but it makes it easier, 1 over n squared, right? So that's going to behave, this is like the integral from 1 to infinity. I could put the 3 halves out here, but I mean, if whether this converges or diverges, it's not going to matter if you multiply it by 3 halves, right? 1 over x squared dx. This and this behave exactly the same way. So if this integral exists, then so does this. Then this series converges. Let's see. That's 3 halves. The antiderivative of x to the negative 2 is negative x to the negative 1 from 1 to infinity. Right? And that's equal to, I'll put the negative to the outside, negative 3 halves times, that's 1 over x, so that's 1 over infinity minus 1 over 1, and that's equal to 3 halves, because this is 0, right? 1 over infinity is 0. So this exists. Therefore, my original sum from n equals 1 to infinity of 3 over 2n squared converges. What does it converge to? Does it converge to 3 halves? Maybe, but this test does not tell us what something converges to. It only tells us if it converges or not. It does not necessarily equal the value of the improper integral, if that improper integral exists. Well, that's interesting. The harmonic series 1 over n diverges, but 1 over n squared converges. And that brings us to the last topic here. Well, almost the last. Is what is a p-series? A p-series is a series of the form the sum from n equals, it could be any, I'm going to put 1 here, but it doesn't have to start with 1, it doesn't matter. I often start with 1, of 1 over n to the p. That's a p-series. So, for example, the harmonic series is a p-series where the p is equal to, what's the p equal to? Right. The p is 1. The other series we did just a minute ago, that's a p-series, where p is 2. I'm going to leave it to you to investigate the proof of this, or you could investigate some numbers on either side. But it's pretty easy to prove, just doing basic integral stuff, like we did in the previous page, that here's a theorem about p-series. a p-series converges for values of p. Now think about that for a second. What do the p's have to be greater than, less than, equal to? What seems to be true here? Well, they don't converge for p equals 1, but they do converge for p equals 2. And it turns out they'll converge for any p that's greater than 1. Equal to 1? No, that's the harmonic series. The harmonic series is so important, and I'm going to keep stressing that because it's the boundary. It's like that line in the sand. If you cross over that line and you get a p bigger than 1, then you converge. If you're on the harmonic series side of that line with a p equal 1 or less than 1, then you diverge. So the harmonic series is like the boundary line between convergence and divergence for p series. So here's an example. Does that converge? I mean, it's not much different than the harmonic series, right? We're just raising things to the 1.1 power. But according to this theorem, the p is greater than 1. Yes. So it does converge. Converges slowly, but it does. So our answer is yes, because it's a p series, and the p is greater than 1. Likewise, if you put a 0.9 there, it would not converge. It's on the wrong side, so to speak, of the harmonic series. Okay, now very briefly, let's talk about the limit comparison test. This is basically a fact that's going to agree very much with what our intuition wants to tell us. I'm not going to go into the proof of or more complicated version of this. I'm just going to show you how it works. Let's say we have a series that looks like this. Something like that, say. Well, think of this from like a pre-calculus limit point of view. As n is going to infinity, which it is, right? What's really going to matter here? What's really going to matter is that the highest exponent is here on the bottom, right? So if you just look at the highest exponents, don't worry about the coefficients, just the highest exponents, this is going to behave, as the n's get really, really big, it's going to behave like what? What p-series? And you pause and think about that for a second. Since the highest exponent here is 2, and the highest exponent here is 3, well, n squared over n cubed is 1 over n. And the 2/3, I mean, whether it converges or diverges, if something converges and you multiply by 2/3, it still converges. If something diverges and you multiply by 2/3, it still diverges. So these coefficients really don't matter. What matters is the highest exponents. So this, no matter how complicated all this stuff is here, if you just look at the highest exponents, this is going to behave like 1 over n. And now we just have to say, oh, well, that's a p-series. And since the p here is 1, it diverges. So this diverges. And then I could do countless more examples, but they all look just like this. It's a very pre-calculus limit kind of thinking here. Very easy. How about n equals 1 to infinity of 4n to the 4th plus 5n squared minus 7 over 7n to the 5.5 minus 3n plus 8. What's that going to behave like? I suppose I should say behaves like, be grammatically correct. That's going to behave like, you can pause if you haven't done that already. Well, the only thing that matters is the highest exponent, top and bottom. N to the 4th over n to the 5.5. There's an extra 1.5 on the bottom. And that's a p-series. And the p is bigger than 1. So it converges. So when we're investigating more complicated looking things like that, they can often, if they're of this like polynomial over polynomial kind of expressions, we can usually just reduce them to p-series and evaluate them like that. And this is officially called the limit comparison test. We won't do the more complicated version of it in 10.5. But now you know. So things behave exactly as we would suspect that they do.